why the most of the UAV affects on torsional vibration, how we can control this torsional vibration by modifying or redesigning the UAV models, and understanding the aeroelastic phenomena and interaction between elastic force, aerodynamic force, and the vibration force which is acting on the UAVs that will sort of by presenting approaches. We'll start now.
Hello everyone. Hello everyone. Actually, the problem is faced by UAV team members. So the person who uses drone. Usually, the UAV drone system is used in surveillance and agriculture, parcel delivery, and defense and disaster management. So basically, the UAV drone, the wings will given torsional vibration. Due to vibration, commonly we use so this problem statement about the UAV drone is faced by the actually this problem is faced by the person who uses UAV. Okay, so basically these UAV drones are used in surveillance, agriculture, parcel delivery, defense application, and disaster management. Like for example, if you go to mines, they also they use as in camera footage, like they use drone. So there is a basic problem in the drone which gives torsional vibration. It means the wing will not be stable. It will be like completely vibrating, so that there are many failures which the sensor cannot give data properly, and also the camera cannot be very stable at times. So these are the negative signs in drone. So according to design thinking, the first step of design thinking is empathize. So what is empathize? Empathize is something you have to face the problems and you have to be in the shoe of the person, you have to solve the problem. So second comes the define. Define is something you have to create the basic problem, what is the problem of it. So in empathize, we have to know what is the problem. So the problem is the problem is torsional vibration. So why this vibration is occurring in that, and what are the disadvantages happen? Next time.
Now let us define the engineering problem clearly. UAV wings are generally lightweight and slender. Because of this, aerodynamic force doing flight can cause the wings to twist around its longitudinal axis. This twisting is called torsional vibration. When the frequency of aerodynamic matches the wing's natural frequency, this can lead to flutter, loss of lift, control difficulties, structural wing failure. So the challenge is, how can we reduce torsional vibration by keeping the wing lightweight and efficient? That is the fourth problem statement.
So yes, now we have a problem. So we have an Ideate solution for it. So they are giving many solutions, like we can use composite. So if we choose composite, we know that it's already lightweight material. Also, it will not corrode. So using composite will give an extra strength and corrosion resistance by using aluminum or any other material. Also, we have a box pad with it. So we know that the angle of twist is inversely proportional to torsional density. So we must have the torsional density higher value. So this torsional density is directly proportional to shear force. We learned in our classes that shear force is directly proportional to thickness. So if you have a larger thickness in the spar, there will be a less angle of twist. So by making the difference in the thickness in the spar region, we can actually make the torsion rigidity higher, so that the angle of twist will be getting less value. So if we do that, means there will be no certain coordination or unique patterns. So next we have the smart materials, like if we can use any actuators or piezoelectric sensors to detect whether any changes in the spars or the tips. So like that we can make a minimum changes. So these are the things we should focus on.
So coming to prototype, we create two wings, conventional wing and improved wing. In conventional wing, aluminum wing with basic spar alignment. In improved wing, composite material using box bar and optimized paper. We designed this wing using the CAD software by applying aerodynamic load using CFD software, perform model and harmonic analysis in ANSYS, measure twist angle and vibration response, build a scaled prototype for wind tunnel testing. This stage helps engineers compare old and new design scientifically.
Yeah, so tested results are the last stage. The improved wing shows 35% reduction in torsional deflection, 18% increase in flutter speed, better camera stability, longer structural life, and lower overall weight. That means the solution is successful. Testing may include wind tunnel validation, flight trials, sensor monitoring, fatigue analysis. This proves whether the concept works in real missions.
So, you people understood how UAV models behave with the aerodynamic load is equal to the structural load, that can be resonance flutter. Resonance makes the structure to change or out of flutter. One is the torsional vibration. To increase the torsional rigidity, you are focusing on composite material, and the environmental property is more dominating for the aluminum. And also you are making the lightweight, and if you reduce the deflection angle, it reduces the torsional vibration, and this will increase the stability of the UAVs. And also using CAD models, you are predicting how much producing the torsional vibration and reducing the flutter effect. So, and you finally said that it has improved around 30% of stability, and this gives the better design of UAVs. So this 5 stages help us to understand how the torsional effects on aircraft or UAVs or drones, which will directly affecting the vibration and especially measuring the performance of sensors or the control surface actuators. These are getting disturbed due to this risk effect. So this is how the short engineers are using this framework to solve the problem. Okay. Thank you.